Good evening, pre-calculus. So I know I promised in our previous live stream that it would be the second to last live stream of the semester. Well, that wasn't quite right because we didn't get through everything that we needed to get through in the last live stream. I had hoped to talk about both the topic of composite and inverse functions and then use that as a way to transition us into talking about exponential functions and logarithmic functions, which is our last type of function that we'll talk about this semester in pre-calc. Well, composite and inverse functions kind of took all our available time in the previous live stream. So tonight is actually the second to last live stream, and this one is going to be about exponential functions. So how are exponential functions identified? How do we compare and contrast exponential behavior with linear behavior, linear being the most basic kind of behavior that we learned this semester? And then once we understand what it is that makes a relationship between two variables follow an exponential pattern, then we'll be able to begin understanding exponential functions from a graphical point of view, from a verbal perspective, looking at data tables, and then last but certainly not least, how do we do algebra with exponential functions? After all, the most challenging thing about exponential functions is that now we're using a new type of arithmetic from our layer cake, whereas before we were just using addition, subtraction, multiplication, and division to define our linear functions, quadratic, polynomial, and rational functions. All we needed were those basic four operations of arithmetic. For exponential functions, we need to go one layer higher and talk about exponentiation and powers. And what makes it challenging is that when I take a power and I raise a number to a power, that operation is not a commutative operation. Unlike addition and multiplication, if I reverse the roles of base and exponent, I get a different value for my exponential expression. And for that reason, there are two different inverses for an exponential operation. One inverse, where the unknown quantity is the base, is something that we're already familiar with. If I don't know what the base is, but I know the exponent, so I have like x to the third power equals 27 or something, I can solve for my unknown base by using a fractional exponent to get rid of the exponent that's up here. In other words, by using a radical or a root. So when the base is unknown, the inverse that we care about is called a root. But it's a much more interesting question about what if I know the base, but I don't know my exponent? How do I solve for an unknown exponent where I might know what the base is? There's a totally different type of inverse for that type of, to undo that kind of exponentiation. And that type of inverse, to discover an unknown base, is called a logarithm. And so our plan for today's live stream is going to be to introduce what exponential behavior in a relationship between two functions looks like. How do we spot it in a data table? How do we spot it in a verbal description? What does it look like on a graph? And then make the transition from there to thinking about different algebraic forms of exponential equations. In particular, what role does the natural base that we call e play in describing exponential relationships? And then to begin to talk about the definition of a logarithm as the inverse operation to exponentiation. Logarithms will therefore let us solve an equation where the unknown variable is trapped up in an exponent. Logarithms will help us rescue that quantity out of the exponent so we can get it by itself and solve for its value. So if you're up late with me this evening and you're my current student, feel free to drop questions that you might have during our live stream in our Slack discussion channel, and I'll try to respond to them there. If you're watching on Twitch, feel free to also drop your questions in the Twitch chat. I'll try to prioritize my current students in responding to any questions that I get over the course of the next hour or so. Tonight is also one of the many presidential debates for the Democratic candidates for president. So if you're watching that and you have one eye on the debate and one eye on our live stream, I certainly don't blame you. After all, it's pretty clear if you're a mathematician who you ought to be supporting in this race for president. Yes, Andrew Yang. I don't actually support Andrew Yang for president, but he's the only presidential candidate ever to think that a hat with the word math on it is his campaign slogan. So not an endorsement, just to point out that that's probably one of the coolest hats I've ever seen. I'm going to have to get myself a copy. Once he drops out of the race, I'm going to get one of those math hats and wear it around just for the novelty value. So what is our plan for today? So we left off in our last live stream finishing up inverse functions. So now we're ready to dig our teeth, sink our teeth dig our heels, whatever, into the topic of exponential functions. What are they? How do we spot exponential behavior? How does it work? So first thing we want to do is talk about how we spot exponential behavior in a set of data and also in a verbal description. So how do we talk about exponential behavior in ways that are similar to but fundamentally distinct from how we talked about linear functions once upon a time. And then in a graphical perspective, we're going to get a little bonus in here. This is something that I think scientists among you are probably more likely to see in your other courses than the business majors among you. But scientists very frequently use this little neat trick to discover exponential behavior in their data sets by plotting it, creating a scatter plot on what are called semi-log axes. So we're going to look at what how we can do that using spreadsheet software to give us a visual cue to behavior that's exponential and not just curvy in some other possible fashion. And then we'll talk about the two different forms of equations we can write down for exponential functions. One of them that directly calls out the base of that exponential function and the intercept, and the second one which re-expresses that base as a power of the natural base that we call e, the number 2.71828182846 ... Some long decimal, but it's just a number, e, between 2 and 3. And so we'll talk a little bit about these two different types of equations for exponential functions. Every exponential function can be expressed in either fashion, and there are advantages and disadvantages to each one. We'll talk a little bit about what those might be. And then finally we get to the algebra part, which is how do we solve simple exponential equations to rescue that unknown variable from out of the exponent using the definition of logarithms. And for today, the bases of the logarithms that we're going to study are not all the bases in the world, but we're just going to focus on base 10 and base e for sort of traditional and computational reasons. The computational reason being that most hand calculators, like this one right here, they'll have a button on them for a base 10 logarithm and for a base e logarithm, but they don't have buttons on calculators for logarithms of other bases. It's sort of an accident of history that the calculator manufacturing industry, the calculator industrial complex, has never seen fit to remedy. So those are going to be the simpler bases we talk about today. In order to go a little bit deeper into logs, we're going to wait until our last live stream, where we're going to really pop the hood on logarithms and find out how the properties of exponents that we remember from algebra translate directly over into properties of logarithms that can help us to evaluate logarithmic expressions with other bases besides 10 and e as well. So that's the rough sketch of what we're going to do for today. So let's get this show on the road by thinking first about how do we identify exponential behavior in data and in words. So how do we spot it? How are we going to know it when we see it? How do we know an exponential function when it shows up? So let's start, as we frequently do, by thinking first about this, what I usually call the rule of 4, right? The 4 different ways in which we can communicate a mathematical idea. And those 4 ways are algebraically, graphically, numerically, and verbally. So we can communicate a mathematical idea using a formula, which we're certainly going to get there. That's going to be our last stop in this journey today. We can communicate using a graph. This is probably going to be our first stop once we get started. And we can, of course, communicate all these ideas in words, and we frequently want to, we frequently have to. Not necessarily just when we're communicating amongst ourselves in our course this semester, but also when we're communicating outside of the mathematical world to people who aren't currently taking a pre-calculus course. How do we communicate exponential ideas using words? But we're going to begin, as we very often do, in the realm of the numerical. So we're going to begin by imagining that we have a set of data points that we're working with. And we want to first understand, if I have this set of 5 data points, and I have only 2 of them that I know my y values for. So when x is -1, f of x, or y if you like, is equal to 6. And when x is 0, f of x is equal to 12. I've got 2 data points. I could plot those 2 data points on a set of axes if I wanted to. And so if I did that plot, I would get a plot that looks something like this. Right here are my 2 data points, -1, 6, and 0, 12. And so there are my 2 data points that come out of this data table. And the first question that I would ask, we're going to kind of do this in an inquiry-based approach. I might ask a question like, well, what number belongs here? Okay. This is kind of a classic mathematical question. It kind of invites you to discover and then apply or make a conjecture as to how you might apply a pattern that we find in this set of data. So what number belongs there? If the value of x is 1, what is the value of f of 1 going to be? And so if I just pose this question to you naively, right, before we know anything about exponential functions, how might we try to discover the pattern that we're observing in this data? Well, my pattern would very likely involve me first looking at my x values and saying, well, there's a consistency, there's a regularity to the values of x that I'm seeing in my data table right here. And the regularity that I'm seeing is that each one of these x values is one larger than the one that came before it. So my adjacent x values are all separated by an addition of 1. So I might say that like this. Like between -2 and -1, I'm really adding 1. And that same addition of 1 also explains the difference between my next pair of x values, -1 and 0, and it's the same as the distance between the next pair, 0 to 1, and it's the same as the distance from 1 to 2. Right? So all of my x values are related one to another by this consistent addition by 1. So that might be the first thing that I notice. And I'll write that up here sort of at the beginning of a sentence. For every increase of +1 in my x variable, my independent variable. So those are the increases that we're seeing represented in my 5 x values that are parts of my data points. So if I want to understand what is happening as a result of these changes in my x values, there are probably going to be changes in my f of x or my y values. And how a function models the relationship between those changes describes for me what type of function that we're talking about. That's why we have different types of functions in pre-calculus and in modeling, because different relationships between changes in our variables are modeled by different types of algebra. So naively, if I want to describe the nature of the change in going from y equals 6 to y equals 12, I have a couple of choices for how to do that. I might choose to subtract, to compare the number 12 to the number 6. And if I subtract 12 minus 6, I get 6. And so one way of describing this change is that it is a change of plus 6 from my first y value to my next y value. So I can use addition and subtraction to describe that change if I want to. And if I did that, then I might complete this thought. For every increase of +1 in x, I might say something like, there is an increase of +6 in f of x, or in y, if you like. I'll just write it as y. So if that's the pattern that I'm observing in my data set, then what that suggests to me is that repeating this +6, every time I add 1 to x, I add 6 to f of x. Repeating that +6 one more time will tell me how to fill in this empty space. And so I'll just take 12 plus 6 and fill in 18. So let's make that our prediction here. And if that's my prediction for how to fill in that y value, then that very same set of change processes can also tell me how to fill in the rest of the unknown values as well. This last y value would be 18 plus 6. 18 plus 6 would give me 24. And then over here I have to go backwards. I have to answer the question, what plus 6 is going to give me 6? And so really, I kind of want to read that one going the other direction. So going the other way here, the opposite of adding 6 is, as you might expect, subtracting 6. The opposite of addition is subtraction. So when I want to take a step backwards, I'll just subtract 6 instead of adding 6. And 6 minus 6 is then going to give me a value of 0 that I would fill in that -2 value. So at the end of all of that process, I have now made a conjecture, an educated guess, right? That if the way that I measure this change between my known y values is that I choose to subtract and find that there is an increase of +6 in my y value that corresponds to the increase of +1 in my x value, then this is how the rest of the data table shakes out. So, if that is my pattern, then what kind of a function am I looking at? Let's look at what happens if I graph all of those data points. Well, when I graph all of those data points, take a look at what the graph looks like. This graph looks like a straight line. In fact, based on the information that we had in our chart right here, we can directly read off the slope and the y-intercept of that straight line. In particular, the slope is going to be the ratio of the change that we have here in y to the change that we're observing up there in x. And so the slope of this relationship is going to be 6 divided by 1, and 6 divided by 1 is going to be 6. Similarly, we can also read off the intercept. The intercept is going to be 0. So if I want to, and I'm going to draw this in our graph right away right here, we could write y equals, oh no, I'm sorry, the intercept is going to be the y value when the value of x is 0. So the y-intercept is right here, is 12. So the slope is 6 over 1, or 6. The y-intercept is 12. And so y equals 6x plus 12 is going to be an equation for this linear relationship. And sure enough, the equation y equals 6x plus 12 indeed passes through all 5 of my data points. Okay. So far, the assumption that we measure this change by subtraction and addition leads us to a linear relationship. So I'm going to write that in the verbal column, and then I've got a question in the Slack channel that I want to try to respond to before we go any further. So when addition and subtraction in x, correlate to addition or subtraction in y, then we're going to get a relationship that is a linear function. The function y equals f of x is linear. And so its graph ends up looking like a straight line. Okay. If I were to have that type of relationship between my changes, I could also not only go forward in the x direction in my data set, but I can also go backwards. So the question that we have here in the live stream is, do we have to move in a positive direction for x's, or could we also go in a negative direction? We can certainly go in a negative direction as well. Let's suppose, just for the moment, that I also had another unknown x value. Let me add one more into my chart right here. Let's say I wanted to know what's the value of x, or what's the value of f of x for x equals -4. So for that, I would want to again measure the difference between my x values by subtracting. And I'd subtract -2 minus -4. -2 minus -4 is +2. Or another way to say that is -4 minus -2 is -2. So how I'd go backwards is I'd say that this is really, I'm subtracting 2 from this x value to get that x value. But let's think about what happens when I subtract 2. It's the same as subtracting 1 twice. So I'm going to kind of take this change, I'm going to break it apart into 2 separate changes. So I've got subtract 1 and then subtract 1 again. But as we were seeing down here, every time I move to the left by 1, every time I subtract 1, I should be subtracting 6 from my y value. And so if I want to move to the left twice, every time I subtract 1 from x, I'm going to subtract 6 from f of x. And so I'm going to go 0 minus 6 and get -6, and subtract 6 one more time, I'm going to get -12. And so the y value for x equals -4 would be y equals -12. Let's add that into our data table just to make sure that we can believe our lying eyes on this one. So when x is -4, we predict y is not +12, but -12. Scroll my graph up a little bit. Sure enough, there it is. Okay. So anytime we have addition or subtraction in x consistently related to addition and subtraction in y. The function y equals f of x is going to be linear. So that is what it meant for a function to be linear once upon a time, right? And the ratio between these changes is called the slope. So let me record that in here as well. The slope is the ratio of the changes in y, let's say differences in y, the changes that we measure by subtraction. Difference in y divided by the differences in x. Right? Okay. So, enough beating around the bush. If that's what linear is, and if we're already comfortable with that being the meaning of a linear relationship, how could we possibly conceive differently? How could we assess the change between my y values in a way that doesn't involve subtraction and addition? So, how do we think differently about the change that's happening from the y value of 6 to the y value of 12 that's going to correlate to this increase of +1 in the x variable? So the first time we compared these quantities by subtracting. What that did is that gave me an amount change. A difference is an amount, right? If f of x is measured in thousands of dollars, then the difference between $6,000 and $12,000 is 12 minus 6, or a $6,000 increase. It's an amount increase. But the other way to measure that change is, instead of using subtraction, I'm not going to use subtraction. Instead, I'm going to choose to divide. And that one seemingly small difference, that different choice in arithmetic, is going to completely explain the difference between an exponential function and a linear function. So now I'm going to describe this change not by subtracting 12 minus 6, but instead dividing 12 by 6. When I divide 12 by 6, I get 2. And the way that I can interpret that is that when I move from this y value to that y value, what I'm doing is I'm multiplying f of x by 2. So, rather than saying that there's an increase of +6 here, I'm going to say there's an increase of multiplication by 2 in my y quantity, right? And another way to say that, so from an English language perspective, we'll often call that an increase by a factor of 2. So anytime you use the words factor of, we're talking about a change which happens by multiplication. Increase by a factor of 2 is another way to say that, right? And that really puts a whole different spin on the set of data that we're looking at, because it's now going to give us a new way to continue our data set and try and figure out how to fill in these other missing data points. So if we go back to the question, how do I fill in this unknown value? Now, instead of having a addition by 6 being the change that we want to repeat over and over again, now we're going to use multiplication by 2 instead. Multiplication by 2. And so in this viewpoint, I'm going to fill in this empty space by using 12 times 2, or 24. And already we turn up a difference between the model that we were looking at first, which turned out to be a linear model, and the model that we're looking at now. So how does that look differently on our graph? If I decide that 24 is my value here, now take a look at what my purple data points are doing. My value of 24 ends up being higher than the corresponding linear model value that we had, which was 18 at this point. Let's continue that pattern. If I continue that pattern a little further, then I'm going to multiply by 2 one more time. 24 times 2 is going to give me 48. And I'll add 48 into my data set. And what we find out here is that we're getting really significantly different kind of behavior now. It looks like my purple data points, these are the ones that I'm modeling now, using my multiplication to model my changes instead of addition and subtraction. We're getting a very divergent set of behaviors happening here. Let's go back to our data table again for a minute. How do I go backwards? I'm going to return to the question that popped up in the live stream here a minute ago. If we think of this as going backwards instead of going forwards, subtracting 1 instead of adding 1, then if when I go forward by 1, I multiply by 2, when I go backwards by 1, I need to do the opposite of multiplication by 2. And the opposite of multiplication by 2 is, you guessed it, division by 2. So when I go backwards, I'm going to divide by this number instead of multiplying by this number. 6 divided by 2 indicates to me that how I would fill in this empty space is there I would want a y value of 3. When I add that data point onto my graph, take a look at how, again, we're seeing a different picture emerge here. Then when I follow my purple data points, we get, again, very different looking behavior. Last thing I'll do is I'll go back to this missing data point for x equals -4. For that, I would need to take 2 steps back. And every time I take 1 step back, I'm going to divide by 2. So here I have to divide by 2 twice in succession to take 2 steps back. Divide by 2 once, I'm going to get 3 divided by 2, which is 1.5. And I divide by 2 once again. 1.5 divided by 2 is going to give me 0.75, or 3/4. And I'll fill in that data point. And here are our 2 different models that have emerged. So my green data points, let me actually change the color on this to green just so that it matches up with the data points themselves. So my linear model that we're looking at, when we were imagining that all of our changes in the y-coordinate were explained by addition and subtraction, once upon a time, whoops, sorry, I'm trying to. So when addition and subtraction explained all of our relationships between the changes in x and the changes in y, we got the linear function that we're seeing here with this dotted line. But there's a different type of function that models the purple data points. And as you might expect, just like with the linear function and its slope, for the functions that we're talking about now, where addition and subtraction in my x variable is correlated not to addition and subtraction in the y variable, but this time multiplication and division in my y variable, multiplication and division in the y variable, then this function is no longer a linear function. Its graph is not a straight line. Instead, this function is called an exponential function. And of course, that is the type of function that we're studying today in this live stream. And every exponential function has parameters that are much like the slope and the intercept for linear functions. As with linear functions, the parameter that we call the intercept is once again the value, the y value of my function when the x value is equal to 0. So in our example, the intercept is just the value f of 0. It's the value of y when x is equal to 0. And we can read directly off of my data table that my intercept for my exponential version of this function, just like for the linear version, is 12. But it's the other quantity that's really interesting. The other quantity is called the base. And the base of an exponential expression is an answer to the question, when x increases by 1, when x increases by adding 1 to it, comma, by what factor does y increase or decrease? By what factor does y change? The answer to that question is called the base of our exponential function. And so just from the data table that we're looking at right here, we've actually already answered that question. It's sort of staring at us in the face. Because my data points, -2, -1, 0, 1, 2, the x values are already separated by +1s. +1, +1, +1. And so we can directly read off the base of our exponential equation as the factor by which y is being multiplied every time x is increased by 1. And in this example, every time x is increased by 1, y, or f of x, is being increased by a factor of 2. So in our exponential equation that we're working on now, the base is equal to 2. So the intercept is 12 and the base is 2. So I'm going to write in our exponential equation for this in secret real quickly here, so you can't see me typing for the moment, because I want us to go through the trouble of discovering how to come up with an equation that actually models this type of behavior. But I'm going to, first of all, let me just, whoops, I want to show you the graph, and then we'll talk about the equation second. So here's what the graph ends up looking like. Bing, right? So here is the graph of our exponential function that came from the data points that we filled in, right? And the way, once again, to understand what's going on here is that every time my value of x increases by 1, for example, from -1 to 0, the value of y is increasing by a factor of 2. So 6 times 2 becomes 12. Then when x increases by 1 again, y increases by a factor of 2 again. 12 times 2 is 24. And then increase x by 1 more time, from 1 to 2. The value of y increases from 24 to 24 times 2, or 48. So that's the reason why the base of this exponential expression is called 2, is that every time x increases by 1, y is multiplied by a factor of 2. So there's what the shape of this graph looks like. And unlike a linear equation, the graph is not a straight line. It's a curving, it's a curved path this time. But like a linear equation, this curve has a constant directionality of change. This curve is always increasing on my graph as we read from left to right. Just like for the linear function, the graph of that linear equation was also always increasing from left to right. So at least we still have a model for this behavior that is monotonic. It always goes in the same direction. So how are we going to come up with an equation that describes this behavior? Well, like with our linear functions, let's start with the y-intercept. Let's start with the number 12. How do I get from x equals 0 to x equals 1? I just have to multiply 12 by 2 a single time, right? 12 times 2. How do I get to x equals 2? I have to multiply by 2 one more time, so that this 48 comes from 12 times 2 times 2 again. Or in other words, 12 times 2 squared. If I had one more data point at x equals 3, my data point at x equals 3, the y value would have to be 48 times 2 one more time. 48 times 2 would be 96. So if let me scroll this down a little bit so we can see that data point. How would I have gotten this 96? I would have to multiply by 2 one more time. So starting from 12, I would have to multiply by 2 once, twice, 3 times to get out to x equals 3. So the picture that's emerging is that the equation for this graph is y equals 12 when x is equal to 0. But for every x that's not equal to 0, we have to multiply by 2 x many times to find the value of y at that point where my x-coordinate is x. Right? So here is what I would call a base-intercept equation for this exponential relationship. And so just to drive my point home here, the intercept of this equation is 12 because 0, 12 is a point on the graph, right? The y-intercept of this graph behind my head is the point 0, 12. And the base of this equation, let me just hide my head for a minute here so we can see what I'm typing. The base of this equation is 2 because every time x increases by 1, y increases by a factor of 2. Right? Y is multiplied by 2 every time 1 is added to x. And so that's the story for how we spot exponential behavior, is that addition and subtraction changes in the x variable are consistently correlated to multiplication and division changes in the y variable. So that's what we have here. When this is an exponential function, we've now discovered a formula for this exponential function. Y equals 12 times 2 to the x. And my x here is up in the exponent. According to the order of operations, remember, if I'm evaluating this expression, the power, the exponent, 2 to the x happens first. And then after 2 to the x happens, we multiply that result by 12. And in the base intercept formulation, this 12 right here is our intercept. And the number 2, sitting right here, that's my base. So that's how the base and intercept get into and out of this, this equation form that we have happening over here. Right? And so finally, from the graphical perspective, we spot exponential behavior. First of all, I'm going to nudge our viewing window up here for just a minute. We can spot exponential behavior just by recognizing that every time my x value increases by a fixed amount, so +1 for example, if I have a bunch of those changes in my x variable, +1, +1, +1, let me add one more in here. And so if all of these x changes are +1s, +1, +1, +1, okay, then if this is indeed an exponential function, all of those changes are going to be correlated with y changes, which are increases in this case, or decreases in a different case, by the same factor every time. So multiplication by the base, multiplication by the base, multiplication by the base, multiplication by the base, multiplication by the base. And so one thing that we notice here is if the base of my exponential expression is greater than 1, what happens to a number when I multiply it by something that's greater than 1? It gets bigger, right? So if the base of this exponential expression is greater than 1, then what we have is exponential growth. I have an increasing exponential function as we go from left to right. Conversely, if the base is less than 1, but we're also going to cap it at 0. So we'll never talk about negative numbers being bases. We can, if you're interested in why that is, we can talk about that, but I'm not inclined to do that right now. If the base is between 0 and 1, what happens when I multiply a quantity by a number that's less than 1? Like if I multiply something by 0.5. If I multiply something by 0.5, it gets smaller. And so that models a process that rather than being exponential growth, rather than an increase over time, we would have a steady decrease over time if my base is between 0 and 1. So that's the story for how we spot exponential behavior in data and in words, and also how we can discover the base intercept form of an exponential equation. So let's move forward off of that and talk about, probably if you've been exposed to exponential functions before in some fashion, then one of the big concepts that you are probably, have some familiarity with from your last exposure to exponential functions, whenever that was, is the scary number called e. So what I actually want to do is just real quickly talk about what the number e actually is. Like why does it exist? Why does it sort of matter? And so for this, sorry, I'm just trying to pull up here the right reference. Yes, I think, yeah, let's go to this one. So let's just, for the sake of mathematical history and completeness, and just for a little piece of mathematical culture, I want to take just 2 minutes and take a look at a video produced by a YouTube channel called the Math Center that introduces us to what the number e actually is and sort of where it comes from a mathematical perspective. So this is only going to take 2 minutes. Let's watch this video together.
We've made a video about pi, the ratio of a certain diameter. But there's a less famous but equally fundamental number known to anyone who's taken high school algebra. It's about 2.718281828459045 and so on. And it was first defined by Jacob Bernoulli, but later Leonhard Euler called it E, and the name stuck. Bernoulli first defined E through compound interest. Now, compound interest says that you get a little bit of money in interest every period, and that money you gained helps you gain even more interest next period. In other words, your interest compounds. So if you stick $1 into a bank account with a 100% interest rate compounded annually, you'll get $2 at the end of a year. If it's compounded semi-annually, you'll end up with $2.25. Quarterly, and you'll end up with $2.44. Monthly, $2.61. Weekly, $2.69. See where we're going? If you increase the number of compounding periods a year towards infinity, then you'll get closer and closer to E dollars. In statistics, it describes the most important statistical distribution, the normal. In biology, it models populations of species through the logistic function. In physics, E describes the exponential decay of a radioactive material. So, while E may not be as famous as pi, it's easily as fundamental and immensely important.
The number pi is equal to 3.14159.
All right. So that's sort of a short explanation for where the number e comes from. Compound interest tends to be the way that e is most frequently motivated, but there's a really good reason in calculus next semester why the number e is more special than the other numbers that we might use as the base of an exponential function. So don't be too scared of the number e, even though we use a symbol to represent it rather than a decimal number. Just think of it as a number. It's something between 2 and 3. Let's take a moment and look at how we might take this algebraic formula that we got for our exponential relationship from down here and re-express it using the number e instead of having my base be the number 2. So, and this is a little bit of a prelude to what we're going to talk about in a few minutes from now. What I want to do is I want to re-express the base of my exponential function as e raised to some power. And then I'm going to raise that number to the x power. I'm going to multiply it by 12. And I'm just going to come up with a different way of expressing my same function that we were talking about here before. So how are we going to make this connection? Well, what we really need to do is we really need to answer the question, e to what power is equal to 2? E raised to what power is equal to 2? Okay. So from here, let's see, I gotta find my little cheat sheet here for a moment. So here's a bit of a preview to what we're going to talk about in a little while, because we've given ourselves here an equation in which the exponent is unknown. So that x that's upstairs is, or sorry, that blank space, that question mark, is a number that I don't know. Whereas the value of the whole power, 2, I know, and I also know the value of my base. It's this number e, right? And so what I really want to do somehow is I want to solve, I'm going to translate over into, sorry, let me get my thing ready here. All right, so this is worth it, I promise. Okay, great. So this is the situation that we're in, right? We have e raised to an unknown power is equal to 2. How do I rescue this question mark from out of the exponent and get it down onto the base in order to isolate it, get it by itself so that we can solve this equation? Well, the key is to rearrange this exponential equation into what's called a logarithmic form. And this is nothing more than the definition of what logarithm even means. If e to the question mark is equal to 2, then that question mark is by definition equal to the base e logarithm of the number 2. That is what we mean by a logarithm. So all a logarithm is it's a way of rewriting an exponential equation in an equivalent form, just by reversing the roles of the question mark, which is unknown, and the 2, which is known. It's a bit like reversing the roles of x and y in a function. And this is why we talked about composite and inverse functions in our previous video, because what we're really endeavoring to do here is we're really kind of just trying to reverse the roles of x and y in the expression e to the x equals y, right? Because if I know the value of y and I'm trying to discover the value for x, then what I really need is an inverse that can tell me, instead of how to turn an x into a y, if I reverse the roles of x and y, how do I turn a y into an x? So the logarithm is nothing more than, by definition, a way of reversing that relationship, right? A way of turning y's into x's that gives the equivalent relationship to having the x up in the exponent, right? So if e to the power x is equal to y, then by definition, x is equal to the base e logarithm, that's what this thing is called, of the number y. So coming back to our the question that we were working on, right? X was my unknown exponent that we're looking for here. Y is the number 2. And so if I want to know how to fill in that question mark, what I'm trying to do is I'm trying to take the base e logarithm of the number 2. So that means that this question mark is, by definition again, the base e logarithm of the number 2. And your calculator can tell you what a base e logarithm is. Base e logarithm is otherwise known as the natural logarithm, ln. So that's the abbreviation for the base e logarithm on a calculator. So it's the natural log of 2. And so that's something that we can just pull out a calculator and just do that right off the bat. So I'll just type in a 2, and then I'm going to hit this button that's up here, right there on this calculator, the natural log button, the ln. I hit that button, and it turns my number 2 into a decimal. The decimal 0.693147, etc., etc., etc. Right? So it gives me a nasty number, but that nasty number is then how I would fill in this blank, ln of 2, which is approximately 0.693, okay, as a decimal. So that is how we would translate this equation from the original base intercept formulation into one that uses an e to the r, e to the rx type of formulation, right? We just need the natural log. By definition, that's what natural log is it helps us to figure out how to fill in this missing exponent that's attached to my e. Right? And so don't forget this little animation. I'm not going to let you forget it, right? All that a logarithm is it's a way of reversing this relationship. It's a way of rescuing a quantity that's trapped up in an exponent by bringing it back down onto the line by itself, right? E to the blank is equal to 2 when blank is equal to the base e logarithm of 2. Right? I hope you see this little animation with your eyes closed and in your dreams tonight, because this is probably the most important thing to know in this entire last chapter of our course, is how to convert back and forth between an equation that's in exponential format into an equation that's in a logarithmic format. So that's big business. Okay, so that's going to close out this first example of exponential behavior. What I want to do now is I want to move on to one last example here, where the behavior that we get from our data set doesn't exactly follow an exponential model, but which does kind of close enough that we can use technology to discover an approximate exponential relationship. And then we're going to get our introduction to logarithms to help us answer some questions about that relationship. So here's where this last example begins. The last example begins with a set of data. And what this set of data is relating for us is it's showing over time a data set. This data set was collected from British Petroleum, so BP, back in the 1980s and 1990s. And because BP is a large energy corporation, they were keeping track of the total production in the United States of solar energy. So how many megawatts in total of solar energy cells were being produced by U.S. companies in each of these years, starting in 1982 and running up through 1999. So this data set is a little bit old. You might imagine that this number is a lot higher nowadays than it was back in the 90s. And you'd probably be right. So how could we use this data to discover a model and then use that model to make predictions about how the production of solar cells is actually progressing over time? So what I did is I just took all of these data points and I entered them into Desmos, into a Desmos grapher. But I'd also kind of like to, I don't know if there's a way to do this off of Desmos or not. I guess not. I'd like to get them in a spreadsheet, but I guess we can't quite make it there yet. We'll look at doing that next. Actually, I think I still have it up here. Yeah, here we go. So this is where this data set came from. It actually came from a web page on the Seattle Central Community College, where they were doing a exponential behavior example for a math class similar to ours, probably. So I'm actually going to take a moment and also open up a spreadsheet and enter that data into the spreadsheet as well. So here's my value of x, here's my value of y, and my x's here are the year, and y is the solar energy production in megawatts. Okay. So here's this data in an Excel file as well. Okay. So actually the first thing that I want to do real quickly is let's make a scatter plot in our spreadsheet of this data. But first, just to make life, let's leave it the way it is. I don't want to get down the rabbit hole too far. So in my Google Sheet here, to make a chart, I'm just going to choose Insert menu. I'm going to go to Chart up here. Let me try and zoom in on this a little bit so you can see better what I'm doing. Just get my window adjusted here a little bit. So if you're using Google Sheets to create a plot of a data set, what you'll want to do is just highlight all of your data set, like I've done here. So all of my x and y values, I've highlighted them with my mouse. And then I'll go to Insert, and I'll choose to insert a chart. And the type of chart that I want to insert here, anytime we're graphing behavior that includes x's related to y's, the type of chart that I want to use is not a line chart, but rather a scatter chart or a scatter plot. So I'm going to scroll down here and choose scatter as the type of chart that I want to see. And once I do that, my Google chart is nice enough to give me the whole picture here. So here's that same graph that we were seeing in Desmos just a minute ago. So here's a neat little trick that I want to expose you to, because this is very often a way that you can spot exponential behavior in a measured data set. So it certainly looks to my eye like this data is not following a straight line. My scatter plot looks like it sort of bends upwards as we read this chart from left to right. So maybe this is well modeled by an exponential function rather than a linear function. But how can we tell whether this is measured well by an exponential function and not by some other function that might curve upwards, like, I don't know, a polynomial or a rational function or something else? What makes exponential functions stand out as being special when we're looking at them on a graph? What makes their curve different from other curves? The way to spot it is actually to take the scale on the vertical axis, which right now, this scale is measured out by equal differences. right? Each of my horizontal grid lines is separated by an equal difference, in this case, of 20 megawatts of power produced, right? 0, 20, 40, 60, 80. We're just counting by plus 20s every time on my y-axis. But remember what it was that defined exponential functions behavior in the first place. I'm going to go back to our verbal description. Our verbal description was that an exponential function is when addition and subtraction in my x quantity correlates not to addition and subtraction in the y's, but instead to multiplication and division in the y's. So I should be able to spot that if I can create a scale on my vertical axis, on my y-axis, that instead of representing equal distances as equal differences, I want it to represent equal distances as equal ratios. So I don't want to count by plus 20, plus 20, plus 20. I want to do something like count by times 2, times 2, times 2, or something like that on my vertical axis. So getting an axis like that is called getting an axis on a logarithmic scale. So what I did is I just double-clicked on my vertical axis here. And in my Google Sheets window that pops up here, what I want to do is I just want to choose this checkbox right here that says log scale. And what that does is it transforms the scale on my axis so that instead of counting by pluses, I'm now counting by times. So equal distances are now represented by equal ratios rather than equal differences. And I'm now going to just rescale so that I go from, I don't know, 2 to 256 or something like that. And once I do that, what we see now is that except for this sort of up and down behavior that we're seeing happening on this side, it does kind of look like eventually what's happening here is that my data set now kind of looks more like a straight line. I want to toggle that back and forth real quickly here just so we can see what happens. So on a logarithmic scale, let me scroll this over a little bit. On a logarithmic scale, my data looks like it does follow a straight line. But on a non-logarithmic scale, it looks like it bends upwards significantly. Log scale, it looks like a straight line. Not a log scale, it looks like it bends upwards. So we can spot an exponential function by scaling the vertical axis to have a logarithmic scale. And if it has a logarithmic scale, then our data will be a straight line, okay, for a function that's exponential. So that was just a little bit of computational wizardry. If you're a scientist, particularly if you're a biologist or a chemist, this is very often the way in the lab when you collect data and you want to know what exponential rule does this behavior follow. You'll graph it on a set of graph paper that's like this. It's called semi-log graph paper. Semi because one of my two axes is graphed on a logarithmic scale, whereas the other one of my axes is on a typical traditional linear scale. Okay, so that's step one, right, is that we can kind of spot that this behavior looks exponential because on a semi-log piece of graph paper, it looks like we have a straight line. If I want to find an exponential function that actually models this behavior, I can use technology to do that. What I'm actually going to do first, though, is I'm going to rescale so that my x value is maybe measured in years since 1980 or something like that, just to make my x value smaller. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I actually don't want to see those. So I'm just going to change it so my x variable is not the year, but now the number of years since 1980. And then I'm just going to have Desmos just perform my linear, not my linear regression, but my equation of best fit. And the model that I'm going to give it for an equation of best fit is I'm just going to type in y equals a times b to the x. So I'm going to try, let me zoom in on it a little bit here, I'm going to try to get it to come up with an equation that follows the base intercept format. There's my intercept I'm trying to find, the value of a, and there's my base that I'm trying to find, the value of b. So if I give Desmos that equation model, then what it does is it helpfully pops out a value of a and a value of b. So I'm going to write this on a blank screen, so you're not going to be able to see this for just a quick second, but bear with me here. So the function model that we got was f of x equals a, which is 1.928, times b, which is 1.2069. I'm going to round that to 1.207 to the x. Okay. So here is the equation that our Desmos grapher here has given us as the exponential function of best fit for the data that we have here in this chart. So we can use this function now to do stuff. But before we do, I actually want to, because we've only talked about so far one type of logarithm, the logarithm that has a base of e. What I want to do is take a moment just to rewrite this in the other form, rewrite it in the exponential form that has a base of e instead of a base of 1.207, right? So we're going to do the same little trick that we did before, where I want to know 1.207 is equal to the magical natural number e raised to what power? And then we're going to have x as the exponent right here, and then I'm going to have 1.928 as the intercept sitting out in front. And so once again, just like before, in order to fill in this blank, I need to answer the question, e raised to what power is equal to 1.207. And so we'll come back to the strategy that we used before, which is an answer to the question, how do I rewrite an exponential equation in logarithmic form instead? Where here the unknown power is 1.207, and before it was 2, right? So let's do that little switcheroo. I've just got to change a couple things here. Sorry, I'm doing a couple behind the scenes things real quickly. Okay, so let's figure out how to solve that equation by doing the same rearrangement that we were talking about before. So if e to some unknown power is equal to 1.207, then that means that that unknown power is the base e logarithm of 1.207. Remember, that's nothing more than the definition of what a base e logarithm means, right? So e to what power is 1.207? That power is the base e logarithm of 1.207. So that's the thing that we now need to evaluate. So question mark is the base e logarithm of 1.207. And base e logarithm is just another name on your calculator for the button that's called ln, the n standing for natural. The natural logarithm of 1.207. And so the natural logarithm of 1.207, I'll evaluate that, again, using technology. It's going to be some nasty number. We'll pull out our calculator, 1.207, and then we'll hit the ln button, and we get, well, all right, scientific notation, wait a minute. Yes, 0.188138. Let's call it 0.19. About 0.19. Okay, so this gives me now a new formula for my exponential function. 1.928 times e to the power 0.19 times x. Okay, now before we go any further with this, let's take a moment to pull out the base and the intercept of this equation and interpret what they mean back in the context of my original data set, right? Remember that my original data set was correlating together two quantities that had some context attached to them, right? My x quantity was measuring a year, right? And my y quantity was measuring the total solar cell production in the United States in a given year, y, right? And my x value, eventually, we decided to measure in years since 1980. So let me write that up here. So my f of x value, this is y, right? This is the solar cell production in megawatts. And my value for x, this was the number of years since 1980. Whoops. 1980. Okay, so how do we interpret an intercept, the y-intercept? Well, just like with any y-intercept, the y-intercept measures the value of y when the value of x is equal to 0. But the value of x is 0 when we're at years since 1980 is 0. In other words, we're at the year 1980. In 1980, and the value of y is therefore the solar production in megawatts. And so this number 1.928 tells me that in the year 1980, the production of solar energy in the United States was 1.928 megawatts in total. Right? So that's how we interpret the intercept of this equation. Now let's talk about the base. And then we'll get on to the algebra of how to use this model. Right? This base, remember, tells me, if we go back to the interpretation of exponential functions that we settled upon, right, where exponential functions came from, the base of an exponential function is an answer to the question, when x increases by +1, by what factor is y going to change? And with that lens on this question, we now understand how to contextualize the base 1.207. It's an answer to the question, when x increases by 1, y is multiplied by 1.207. That's going to kind of be my shorthand here. But what does it mean for x to increase by 1 if x measures the number of years since 1980? Well, when x increases by 1, we can kind of say every year that passes, y gets multiplied by 1.207, but y is the solar production in megawatts. So let me clear out some space over here. For every year that passes, the solar production increases by a factor of 1.207. That's usually not how a multiplication change is expressed in sort of popular culture and popular media. Very often, when we have a change which is represented by multiplication, we'll represent that change by a percentage instead. So we could also say here, increases by, well, if I multiply something by 1.207, that's the same thing as multiplying it by 120.7%. Just moving the decimal spot 2 positions to the right. But if I multiply something by 20.7%, 120.7%, that's the same as adding 20.7, so take that 100% away. It's the same as adding that 20.7% to my original amount. And so this is usually how a multiplication change is reported in popular media. We'll say something like, every year that passes, the solar energy produced in the United States increases by 20.7%. That's what having a base of 1.207 actually communicates to us about this exponential relationship. So there's my exponential function. There's a contextualization of the base and of the intercept. Now, let's take this opportunity to do just 2 algebraic things to wrap up today's live stream. So what are we able to do with this model now that I have an actual function, an actual equation that gives us a model for this behavior? So 2 questions. First of all, what does this model predict the solar production will be in the year 2020? So that's question number 1. Okay. And then question number 2 is going to be, when will the solar production reach, I don't know, let's say 1,000 megawatts? So 2 questions. And notice the difference between these 2 questions. On the one hand, my first question is, one in which we know the year, right? So we know the value of x. X is known. And we're just trying to find y. Whereas the second type of problem is one in which the y value is known, but we want to know what x is. And so that makes these two fundamentally different types of problems. So let's start over here. When I know my value for x, x is supposed to correlate to the year 2020. The year 2020 is going to be 40 years since 1980. So x is equal to 40 in my first example here. And so the question is, how much solar energy is going to be produced in that year? In other words, my y is what I'm looking for. Y is unknown. And my y is equal to f of x. But my x value is 40. And so to answer this question, I just have to evaluate f of 40. And that just means replacing the value x in this exponential expression with the number 40. So let me use this version of my formula. It's going to be 1.928 times e to the 0.19 times 40. And as long as we are careful with our order of operations, we can evaluate this expression pretty quickly. The first thing I would do is multiply 40 times 0.19. I'm doing that first because it's trapped in the exponent, which is acting here like a grouping, a set of parentheses around this 0.19 times 40. So I'll do that bit first. 0.19 times 40 is, let's see, that's going to be 7.6. I hope I have that right. Let me just quickly try that on my calculator. 0.19 times 40, 7.6. All right, shouldn't doubt myself. And then the next step is I need to take that 7.6 and I need to do e raised to that power. So I have a button on my calculator that's the e to the x button. I'm just going to hit that button and it'll turn my 7.6 into e to the 7.6, which is approximately that number, 1998.2. So it becomes gigantic, 1998.2. And then I just need to multiply that by 1.928. And so roughly the value that I'm getting here is 3,852. And then that would be measured in megawatts, because those are the units of my my y value. Okay, so for that, all I had to do was evaluate my function for an x value that I know. So that's pretty straightforward, right? We didn't have to do any algebra to do this. The second problem is the one that has the stickier algebra involved in it, because when I know y, but the question is x, and the question here is when, and because x is my when variable, this means that x is unknown. So now what I'm trying to do is I'm trying to solve the equation f of what x is equal to 1,000. Right? So I have an equation now where x is unknown, but the value of y equals f of x is known. Right? The value of y is 1,000. So if I put in my expression for f of x, 1.928 times e to the 0.19x, and then I have equals 1,000. What is my job now? My job is to try and figure out how to get that x by itself. Right? How am I going to rescue this x from all the arithmetic that surrounds it? And there's quite a bit of arithmetic surrounding it, right? I'm going to zoom in on this just to make sure that we can see all of these steps as clearly as possible. So this x, if I'm this x, the first thing that's happening to me is I'm being multiplied by 0.19. Then I'm being exponentiated with a base of e, and then at the end I'm being multiplied by 1.928. So if I want to solve for this x, I need to unwrap those steps in the opposite order. So the first thing I would do is I would divide by 1.928. So we're going to make that my first step here, 1.928. which I would do on both sides of my equation. On the left side, it's going to have the effect of canceling out that 1.928. And on the right side, I'm going to get 1,000 divided by 1.928. Pull out my calculator for that bit, 1.928. And I'm going to get about 518.7. I'm doing a little bit of rounding there. So now we've dealt with this multiplication, which is happening last. I divided away so that it's no longer there. Now, the very last thing that's happening in this expression is the exponentiation with the base of e. And because that's the last thing that's happening here, it's the next thing that we need to undo. How do we undo that expression? Well, again, we are in search of a tool that is going to allow us to rescue the exponent of an exponential expression. Where here, my exponent now is 0.19 times x. And my base is e. My right-hand side here is 518.7. So how do I do it? Well, as you might expect, the answer here is the same as it ever was, right? Which is we can undo an exponential expression by using the appropriate logarithm, right? If e to the 0.19x is equal to 518.7, that means that 0.19x is the base e logarithm of 518.7, right? It's the same interchange of the role of x and y, right? The same interchange between the exponent in an exponential expression and the value of its power, right? We can trade out that exponential form for a logarithmic form instead. Move the 0.19x to the other side, move the 518.7 into the argument of the base e logarithm. So this is how we're going to rewrite this equation. It means exactly the same thing as it used to, but now we've rescued that x from out of the exponent. How we would write that is we would just write it as taking a natural logarithm on both sides. When I take a natural logarithm on both sides, the right side of my equation becomes the natural logarithm of 518.7. And the left side becomes just 0.19 times x. That's the magic step. I'm just going to put exclamation points right there. That's the step where if you get comfortable with that step in your algebra, that's the only new bit of algebra that we're learning here in this last chapter of pre-calc, right? Is how do I rescue that x from outside of the exponent? Because now that we're here, x has been rescued from the exponent. The only thing we have left to do to finish my equation solving is I just need to divide by 0.19 on both sides. And I find out that the value of x that's going to solve my equation is going to be the natural log of 518.7 divided by 0.19. Of course, what is that as a number? Can we get a good estimate for that? Well, for that, all we really need to do is go to a calculator. We'll take that 518.7 number that we had from before. We'll compute its natural log. I hit the natural log button, and I get about 6.25. Then I'll divide that by 0.19. And there's the number that I get out of this process, 32.9. And so coming back to the original question, when is solar going to reach 1,000 megawatts? It's going to happen when x is about 32.9. But let's remind ourselves what x actually represents in this problem. X represents the number of years since 1980. That was our time variable. And so just to finish this thought, right, if x is approximately 32.9 years since 1980, I just have to add 32.9 to 1980 to find out that this really means that this level of production in our model is going to approximately happen in the year 1980 plus 32.9. That's 2012. Great. And that brings us to the end of this example. So if you're looking for the one takeaway, as I've been harping on for most of the second half of this video. The big takeaway is just the new algebra that we learned for how to rewrite any exponential expression as exponential equation as a equivalent logarithmic equation instead. This little dance that we do with the exponent and the value of the power in an exponential expression is such big business. So the more practice that you can get with using this as a strategy to solve simple exponential equations, the better off that you're going to be in the long run. That's going to wrap up today's live stream on exponential functions. We're going to do one more live stream to really go deeper into how logarithms work, properties of the graphs of exponential and logarithmic functions as well, and the algebraic properties of logarithms that can help us to simplify logarithmic expressions and solve logarithmic equations as well. And that's going to be where our pre-calculus course ends in our last live stream. I look forward to that one with you as well.